Hi, and in this MicroVid, we'll be continuing on with the topic of breathing mechanics, and today we'll be talking about pulmonary resistance. Now, pulmonary resistance is a very large topic under breathing mechanics, so if I talked about every facet of pulmonary resistance, this definitely wouldn't be a MicroVid, it would be more of a MacroVid. So we're going to try to keep it short and sweet. So let's begin with the equations that describe pulmonary resistance. So let's zoom in here. So resistance can be defined as the change in pressure over the flow rate. So that's what resistance is. So if we look at this equation here on the left, what we can see from the beginning are the relationships between resistance and a pressure gradient. As a pressure gradient increases, so if you have a delta P, that's the pressure gradient. As you increase the pressure gradient, you'll increase resistance. Now the opposite with flow rate. As you increase the flow rate, you're going to decrease resistance. So it's important to understand these relationships. Now these equations describe resistance in a tube and fluid moving through that tube. So you can't apply these to every situation, but when we're talking about the lungs and the respiratory system, these equations can be applied to that. So here on the right, we have a derivative of Poiseuille's equation right here. So let's define these terms. So this represents viscosity, or the thickness of a solution. This represents the length right here. It's L for length, the length of the tube. And this R represents the radius of the tube. Now, it's really important to understand that obviously length of the tube and viscosity are going to affect resistance. If you increase the viscosity, you're going to increase resistance. Honey has a higher resistance to flow than does water simply because the viscosity is greater. Also, the length of a tube. If you were to pull fluid through a 12-inch straw as opposed to a 50-inch straw, when you pull fluid through the 50-inch straw, it's going to have more resistance simply because the length of the tube is longer. But let's look at the radius here. The radius is really interesting how this works, especially this r to the fourth value. To depict what happens with the radius, since the radius is in the denominator, we obviously know that it's inversely proportional to the resistance. However, this r to the fourth power multiplies or amplifies any changes in radius that we see. So let's scroll down to see what I mean by that. This picture depicts, right here we have a radius, we have fluid flowing through a tube with a radius of 2. Okay, so this radius has 2 and we see fluid coming out of it. The volume coming out of it is 16. Okay. Now, if we were to take this radius, this tube right here, and we were to decrease the radius from 2 to 1, so decrease the radius by 50%, you would think that that would increase the resistance by 50%. But because it's not just the radius, but it's the radius to the fourth in that equation up above, we see that when we decrease the radius by 50%, what happens to the volume is that we decrease it by 16. Okay, so we decrease the volume by 16. So this means that when we have a change in the radius, it's going to alter the resistance to an even greater degree, whether it's increasing the radius or decreasing the radius of that tube. Make sense? Okay, let's move on to the next topic. So here we're looking at resistance on the y-axis, and on the x-axis we're looking at airway generation, so the progression through the airways, through the respiratory system. And what we see is very interesting. We see an initial increase in resistance, and that's at generations 2, 3, and 4. This is because resistance is, if we draw it out here, 8 viscosity length divided by pi r to the fourth power. Now remember that as radius decreases, as the radius of the tube decreases, then resistance will increase. And that's what's happening here. We see the radius of the tube as it's dividing, it's decreasing, right? Because you're dividing and moving to a smaller airway. And the resistance is increasing. So that's what we would expect to see. However, something occurs that we don't expect, and that is at generation, on this graph, it's around 4. So right here at generation 4, we begin to see a decrease, and this is a drastic decrease in resistance to airflow, even though we're moving down the tubes, and the tubes generally are getting smaller. So why do we see this decrease? Well, if we had just one tube right here, if we had one tube and we decreased the radius of that tube to, say, that radius right here, what would you expect to see? Well, you'd expect to see resistance increase, okay? And that's what we see. We see this scenario here in the initial parts of the airway generation. So in the trachea, the primary bronchi, secondary bronchi, we see that increase in resistance. However, what's happening is that as the airways continue to branch, right around the 4th or 5th, we see that the surface area increases drastically, so much so that the resistance is actually decreasing. And let me draw this out for you. So here I've drawn some lungs, and we see the primary bronchi, and we know that the primary bronchi and that branch into the secondary bronchi, they get smaller in diameter, and that's what we see over here with the increasing resistance. However, what's happening now is that there are so many branchings. Those branches have branches, and those branches have branches, and those branches have branches. What's happening is we see an increase in the surface area of these small bronchi and the bronchioles, so much so that it's decreasing the resistance, even though each individual tube is decreasing in its radius. So in order to show this a little bit better, let's look at this graph in your notes. So this is a graph looking at airway area in the red, right here in this dashed red, and then also looking at the velocity in the yellow. So as airway, what's happening right here, airway area, as you progress through the generations, airway area is increasing. And so this area is increasing. What's happening to velocity is actually decreasing. And this makes sense. And we can use the analogy of a river and its branches. And so here I have a river, and if we were to take the velocity of the water at this x right here, we would find that the velocity would be high. So the velocity would be high there, and the total area right there, we'll take that, that's the diameter, but we'll just say the total area would be relatively low. Now as we progress down through the different branchings, what we would see is that individually the area would be even lower. However, collectively, if we were to take a collective measurement across this whole portion right here, what we would find is we'd find the velocity would be, the velocity of the water flow would be really low, but the total cross-sectional area would be really high. This is the same thing that's happening in the lungs. What's happening is you have a decreased velocity because that flow, that air is split up into so many branches, and there's so much area that it actually decreases the velocity. So the area increases, which is going to decrease the velocity. I hope that this has been helpful.